The production of tropospheric ozone starts with ozone, as shown in this chemical scheme. This may appear counterintuitive, but owing to the chain reaction, with the catalyst OH regenerated, several molecules of ozone are generated, leading to an amplification. The degree of amplification depends on the levels of NOx, which are emitted as a result of human activity, mainly through the burning of fossil fuels. It is always good to do an experiment to test a hypothesis, namely that there is a link between the OH radical, sunlight, and the production of tropospheric ozone. In order to show the role that chemistry plays, a solar eclipse is ideal, as the lights are switched out and then back on again fairly quickly, minimizing any effects of changing meteorology which occur at sunrise or sunset. My research group were making measurements in the south of England during the eclipse in the summer of 1999, which fortunately was on a clear day at the field site. The red line shows the intensity of the sunlight that leads to production of the OH radical. It starts to decrease when the moon blocks the sun, not straight away, as the part of the sun that is unblocked still is increasing in intensity during the morning. The sunlight falls to zero at the point of total eclipse around 10:25 GMT before rising again. The OH radical follows suit. When there is no sunlight, it is not made anymore, and as it is removed quickly, its levels fall to zero. This stops the production of ozone, but there is a delay of about 15 minutes owing to the various reactions taking time to occur, and so the ozone drop lags that of OH. This is a complex diagram. Start at the top and follow the sun's rays into the atmosphere, and note what can happen to them. They can reflect from clouds or aerosols, or make it to the Earth's surface, where they are either reflected, usually only a small amount, unless a snowy region, or absorbed by the surface. Radiation is then re-emitted at longer wavelengths, and this radiation either escapes to space or is trapped by greenhouse gases, aerosols and clouds. All these effects need to be included in computer models to predict the climate of the future. Clouds represent the most difficult challenge for climate models. Their behavior depends on many things. For example, the size of the solid ice or liquid aerosol particles they are made of, their altitude and thickness, and modelling clouds represent the largest error in climate models. Two great resources for further reading are the Royal Society and US Academy of Sciences joint report on climate change, and also the fifth assessment report of the Intergovernmental Panel on Climate Change. Also, there are some fun movies out there about climate change. I have provided links to just 3 of these, which I quite like.